thank you very much for the invitation. So I was asked to give this talk to let's say illustrate some properties of a certain type of function, which is a generalization of harmonic functions that have seen a significant amount of applications in general relativity, and also now starting to appear in geometry with comparison theorems. So let me, just to give some background, start the story from where these functions came from and how they arose, and then we'll discuss the applications that have been found so far. Okay, so the basic object of study in mathematical relativity is an initial data set for the Einstein equations, and this consists of a three-manifold with a Riemannian metric and a symmetric two-tensor, which represents the extrinsic curvature or second fundamental form of the embedding into some space-time. And if one takes the traces of the Gauss-Cadazzi equations for the embedding into space-time, you arrive at these constraint equations, which have physical interpretations and also geometric relationships. So this portion here, which we'll call mu, is the energy density of the matter fields. We don't have to worry too much about this for this particular talk, but this is the right-hand side of the hyperbolic Einstein equation, the stress energy tensor, applied to the unit normal for the slice in the space-time. So imagine some slice, and here's normal in space-time. R will denote the scalar curvature of the slice, and then we have other terms involving the second fundamental form. And this represents the momentum density. And the main important inequality that we are going to assume is something called the dominant energy condition, which is a relationship between these two variables. There's physical motivation for this inequality, but geometrically, it's a type of lower bound for the scalar curvature, because R is related to mu, and if it's lower bounded by J, let's suppose, say, trace K is 0, then we immediately have non-negative scalar curvature. And so this is how this non-negative scalar curvature came into play, or is related to mathematical relativity. Okay, so the ADM mass is a natural quantity associated with each initial data set, which is asymptotically flat. So we have a three-manifold at infinity. It's topologically R3 minus a complex set minus a ball. And then we have certain fall-off between the metric and the Euclidean metric, and the second fundamental form will tend to 0. And so we don't have to worry about the specific fall-off conditions, but just intuitively, the manifold is becoming a hyperplane, a flat hyperplane in Minkowski space, for instance. And then we can define the ADM energy and linear momentum as these flux integrals over large coordinate spheres in the asymptotic end. And they were motivated originally by a Hamiltonian analysis of the Einstein equations. This is how the physicists came up with these strange expressions. But from the geometric point of view, you can view this object as being the divergence term in the scalar curvature. So we can think of this as type of a flux of scalar curvature at infinity, and this gives the natural relationship with scalar curvature problems. And the mass is the Lorentz length of the form momentum vector, so E squared minus P squared. So we may work interchangeably between mass and the energy and momentum. And the energy momentum densities are assumed to be in L1 at all times in this talk. So the positive mass theorem, we'll refer here to the space-time version of the positive mass theorem, which is where space-time harmonic functions arose. This simply says that if you have local energy density satisfying an inequality, then the global version of this also holds at infinity between the ADM mass and linear momentum. And moreover, it's has a rigidity statement that if E equals to P, then both must be 0, and then your data arises from Minkowski space. So we can view the difference of E and P. Okay, someone put a...
Yeah, I think the screen sharing seems to have stopped.
Oh, okay, let me...
To your face.
Okay, something happened. Screen sharing. I'll start it again. Is that...
There it is.
Okay.
Coming up.
Okay.
Now you
Um,
need to open your talk again. There.
okay, notice. Okay, good. Um, so we can view the difference of E and P as a type of measure of how far off this initial data set is from being embeddable into Minkowski space. In the Riemannian setting, if E is zero, you get a Euclidean space, R3, the time slice of Minkowski space. So you can view the mass in the Riemannian setting as being how far off. And three manifolds with non-negative scalar curvature R from being Euclidean. So the original treatments of this theorem in the early 80s are due to Shen and Yao. They had a two-step process where they used stable minimal hypersurfaces followed by deformation back to the original case using the Zhang equation. And they were able to establish the E greater than or equal to zero inequality with some extra fall-off conditions for the trace of K. Witten had a modified Dirac operator to handle the spin case in all dimensions. And he was able to give an outline for the case of rigidity, but Bega and Crucial were able to give a rigorous statement for the case of equality using the spinor approach. New proof, fairly, let's say 10 years ago by Eichmer, Huang, Li, and Shang, uses the analog of minimal hypersurfaces in the spacetime setting called MOTS, marginally outer trap surfaces, or apparent horizons. And these are what you can think of as a generalized notion of mu bubbles. And they were able to establish the full inequality, but not with the rigidity statement. The rigidity statement was done later with this approach using Huang and Li, who showed that it followed from the inequality. Two other strategies, let's go to the Riemannian case. Two other strategies for the positive mass theorem were established, one by Ricci flow by Yu Li, and this is the three-dimensional case, and the same Huisken-Elmanen using inverse Mikurich flow also in dimension 3. There are other related approaches to the Huisken-Elmanen approach, but using harmonic functions. Their harmonic functions are asymptotically radial. This is due to Augustiani, Mazzieri, and Aronzio, and also Miao has a separate treatment, and these are somehow related to the inverse Mikurich flow approach. And recently, Lesord, Unger, and Yao have treated the positive mass theorem with incomplete ends. Okay. And there are higher dimensional statements as well, though we won't focus on that in this talk. The MOTS approach extends up to dimension 7, just like the minimal hypersurface approach, and Eichmer has extended the Zhang deformation up to those dimensions for the spacetime version. And there's a Kähler manifold proof for all dimensions by Hein and Lebrun. And then there have been proposals for the higher dimensional case put forth by Locamp, Shane, and Yao for the time-symmetric Riemannian case. Okay, so now we get to the level set approach. So in 2019, Daniel Stern put forth a new way to study scalar curvature in 3 dimensions based on harmonic maps to S1. And he was able to recover basic theorems such that the torus does not emit positive scalar curvature, and also characterizations of S1 cross S2 using the two systole. And the proofs were very simple and straightforward based on an integration by parts formula. And from this, we realized that if you use asymptotically linear harmonic functions in the asymptotically flat setting, the mass will naturally appear. And so then using a similar type of integration by parts formula, we were able to establish a version of the positive mass theorem. So the basic idea of Stern's approach is to consider the original Wagner formula. So if you take the Laplacian of the norm of a gradient of a function squared, you get the Hessian term and a Ricci term. And if we think of this in terms of level sets, the gradient is the normal to the level sets. And so we're calculating the Ricci in the normal direction. If you want to extract scalar curvature from this, you can use the Shane and Yao trick to replace the Ricci curvature using the Gauss traces of the Gauss equations to get a difference of scalar curvature and 2 times the Gauss curvature, which is the scalar curvature of the level set. There are other terms that come out from this, say the second fundamental form and mean curvatures, but those can be written in terms of the function u, and the general formula involves Laplacians in various places. So these terms would go away if you assume you're harmonic. And so you end up getting a formula relating the Laplacian of the norm of the gradient, not the norm squared. It's important just the norm of the gradient with the difference of the two scalar curvatures, okay? And the main point is that instead of having a square here, we are now dividing by one norm gradient. And so we have the Gauss curvature multiplied by norm gradient to the first power. And so at this stage, if you perform an integration and use the co-area formula, the Gauss curvature, which we have no control over, becomes just an Euler characteristic and say geodesic curvature on if you have a boundary for these level sets. So that's the important difference why we cannot use the original Wagner formula. Even if you do the Shen-Yao trig for the Ricci, you need to be able to get rid of the Gauss curvature using the co-area formula. Okay, so that's the main point of this inequality. And so putting those ideas together, that the mass is extracted by asymptotically linear harmonic functions in the flux terms in the integration by parts. We get a formula for the mass, or lower bound, is essentially a formula. In terms of the Hessian, and there's some denominator to this, but we think of this as controlling the Hessian, and the part which tells us that the mass is morally the integral of the scalar curvature. Okay, and something to observe is that we are integrating not over the entire manifold, but over an exterior region. The reason for this, so this is the exterior region, which is diffeomorphic to R3 minus a sequence of balls. If you take the outermost minimal surface, the region outside of this will be of this form topologically. And we need this in order to control the level sets. So as I said, if we integrate the Gauss curvature, we get the Euler characteristic of the level sets. If the Euler characteristic is too big, this will be detrimental to the sign of this inequality in the formula. So we need to keep the Euler characteristic of level sets below 2. Okay, so we don't want spheres. Spheres are the bad topology for these level sets. And we can control this in several ways. So say we have a level set which is homologous to 0, is trivially homologically. Then by the maximum principle in Hopf's lemma, we know that this cannot appear. So a level set means the function is constant on the boundary. If you obtain a max on the boundary, Hopf's lemma says the outward normal derivative is strictly positive, and the minimum would also be on the boundary. You get that the function must be completely constant inside and get a contradiction. The other possibility that could occur that causes problems is when you're homologous to the boundary. Let's say in this situation, we have minimal surface boundary. Then we put Neumann boundary conditions for the harmonic function there in order to eliminate these type of surfaces as well. So in the end, the only type of hypersurfaces that we have for the level sets should be thought of as these extended hyperplanes that somehow foliate the initial data. We don't have compact level sets, and specifically, we don't have them that are spheres. That's the purpose for this exterior region condition. And another important point, something that is different from Witten's formula. You do get a quantitative form of the positive mass theorem using Witten's formula as well. But here, we don't require the non-negativity of scalar curvature in order to obtain this formula. It holds regardless of the sign of the scalar curvature, because we're just solving a harmonic function to obtain this inequality. For Witten's proof, in order to get existence of the spinors, one needs to assume some non-negativity or some positivity in eigenvalue, say, to get existence, to eliminate kernels for the Dirac equation. And in the rigidity statement, we do obtain that the manifold is Euclidean. And the heuristic here, the idea is that when the mass is 0, we essentially have a 0 Hessian. And Hessian vanishing splits the manifold a la the Chir-Gomal splitting theorem. And so if we have 3 asymptotic linear harmonic functions, one going to x, y, and z, we get 3 different splittings, and this gives us Euclidean space. Okay. So I think I mentioned most things here. I just also want to point out that if you do have horizons, you get a non-zero contribution to the mass, and it would be somehow interesting to quantify what is the lower bound in terms of perhaps a Penrose inequality. And one can draw analogies with this type of proof between stable minimal hypersurfaces, as well as I mentioned the Dirac approach. But for the stable minimal hypersurfaces analogy, well, you have a single hypersurface that is used, but in the case of equality, the level sets of the harmonic function do coincide with the minimal hypersurfaces. And so one could think of the level sets of the harmonic function as pre-minimal surfaces, or surfaces that are trying to find the the special minimal surface and that is going to play the important role. Okay. But the advantage is you don't, well, if this approach could be extended to higher dimensions, you don't have to worry about singularities of minimal hypersurface. But so far, there's not been an extension to higher dimensions of this approach. Okay, so some application of this formula. Let's consider the stability question that's received some attention over the past few years. If we have a sequence of manifolds, non-negative scalar curvature, and the mass tends to zero, they're asymptotically flat, this space should converge to Euclidean space in some way. That's what we would like to show. And there are two main conjectures in this direction. One is by Huisken and Ilmanen, which appeared at the end of their paper on the Penrose inequality over 20 years ago. And their idea was that there should be some sets of small size in the sequence that you can extract, and then outside those sets, the remaining manifolds should converge to Euclidean space in the Gromov-Hausdorff sense. And an alternate version of the conjecture, which is stated in a paper of Lee and Sormani, is based on the intrinsic flat convergence. And the hypothesis here is that there are no interior minimal surfaces, and then one should get intrinsic flat convergence. So some previous results on this theorem are due to Lee and Sormani using inverse mean curvature flow type ideas in spherical symmetry. Sakovic and Sormani treated spherical symmetry in the asymptotically hyperbolic realm. Bryden, Sormani, and myself did the spacetime version of this in the spherical symmetry. Graphical cases are due to Allen, Wang, Lee, Perales, and Sormani, and geometric static manifolds also due to Sormani and Stavrov. These are all in the intrinsic flat sense. In the Gromov-Hausdorff direction, for the Huisken-Ilmanen version of the conjecture, we have a result with Dmitry Kazaras and Dan Lee. Here, the main hypothesis is that we have a strictly, a uniform Ricci lower bound here. This is the main hypothesis. And there's also an extra topological condition that we need in order to control the level sets. So with these hypotheses, we were able to get convergence to Euclidean space without extracting any sets in the Huisken-Ilmanen approach. The main idea or the impetus for this result was to try and combine the level set formula for the mass with the Cheeger-Colding almost splitting theorem, the techniques of Cheeger-Colding. And this is where we use the Ricci lower bound. We use the Cheng-Yao gradient estimate, also the segment inequality in very important ways to obtain this result. And again, the idea was that, well, we have control over the Hessian and say type of L2 control over the Hessian. And this was one of the core arguments in the Cheeger-Colding proof. So recently there's been a dramatic development in this direction due to Chonghan Dong and Antoine Song. They were able to completely remove all assumptions. So the Ricci lower bound, they removed this condition. They removed the topological assumption on the second homology, and they found the surfaces to remove. They found some surfaces of small area, and were able to estimate the surfaces in terms of the mass. And this is actually quite interesting. If you notice, this is some small, or they can get an arbitrarily small epsilon, but this is reminiscent of the Penrose inequality in that the mass is boundable by square root of the area for some surfaces. These are not necessarily minimal surfaces. They're actually level sets of a function constructed from the three harmonic functions that do the splitting. Okay. And so this is what the idea of their proof is, essentially to extract squeeze as much as possible out of the mass formula. And they were able to find some very beautiful arguments with isoperimetric inequalities in the mass formula to obtain this result. So essentially the Huisken-Ilmanen conjecture has been confirmed in their work. Okay, so now we come to the main topic of the talk, the spacetime harmonic functions. So if we were using the intuition that the harmonic function approach is somehow analogous to, or the idea is that you can split the manifold using the Hessian, okay, so we're interested in splittings. Here, for the spacetime version of positive mass, it's much more complicated because you don't want to split your initial data. So the initial data, even if you're just in the rigid case, you're a hypersurface in Minkowski space, these things don't split at all. I mean, most of them don't split. So you don't want to look for splittings of the initial data, but rather you want to look for splittings of the space-time that you sit in, okay, in, say, Minkowski space. So with that intuition, wanting to, say, space-timize the previous formula, we look for functions with vanishing Hessian in Minkowski space, so namely linear functions. So we take an arbitrary linear combination of the coordinates in Minkowski space, take a hypersurface in Minkowski space, and now let's restrict this function, this arbitrary linear function, to the hypersurface and see what equation it satisfies. Okay. So since the here we'll take just the trace. This means the trace along the hypersurface in Minkowski space. The boldface means space-time derivative, space-time connection, and so forth. So this will be 0 because these are just linear. And if we write it in terms of the induced connection on the hypersurface and then some extrinsic curvature, we obtain this formula. So the Laplacian of there's a function, but this is Laplacian along the hypersurface, and then we get a trace of the extrinsic curvature, and then the normal derivative of the linear function. So this n is the unit normal to the slice in Minkowski space. So at this stage, we have an equation, but the problem is that this normal derivative is not something intrinsic to the surface. We want an equation that only relies on the initial data itself. So at this stage, we have a choice. We have to figure out what do we want to choose this normal derivative to be. Well, there are several choices. The one that turned out to be most useful was to choose the normal to agree with the gradient. This is the spatial gradient of the function along the surface. And the reason for this is it made the space-time gradient a null vector. Okay, so the length squared of this space-time gradient is 0. Now, the reasons for this, it's not entirely clear, but it turned out that with this choice, one gets a mass formula. So we input different versions of this, and the one that gave the most natural mass formula, gave any mass formula, the one that we could find is this choice. And somehow the null choice is the one that simplifies the geometry the most. And this may be connected to some ideas of Penrose with the null tetrads that he uses to rewrite general relativity, but it's not clear. Anyway, that one worked the best. Now, I could say, and this is some kind of thing that I find interesting, that if we choose other values for the normal, let's say we choose it so that the space-time gradient is time-like or the space-time gradient is space-like. So you get two other choices. You could arrive at an equation like this on the hypersurface. And the question is, what does this do? What does this mean? And it turns out there's, at least for the case here of the time-like situation with the +1, this is reminiscent of the Shenyao-Zhang equation. Now, the Shenyao-Zhang equation was used for a completely different purpose. It was not used to get a mass formula. But the idea is that if you take this square root and divide it under the Hessian, so in other words, take this term, then you have this expression minus Kij, and you're taking the trace of this with respect to the metric, setting that equal to 0. That's just a rewriting of this equation. Now, the Shenyao-Zhang equation is that expression, but traced with respect to the Zhang, a different metric, which is just this one, where you add du squared. So you think of this as a induced metric on a graph in the product manifold, and then you arrive at this type of, let's say, time-like space-time harmonic function equation. And well, we don't know what this is useful for in terms of level sets, level set approach. We don't have a mass formula for this, but at least for Shane and Yao, the purpose of this equation was to deform the metric or the initial data to a place where you get almost non-negative scalar curvature, but say weakly up to a divergence term. So in fact, there is a formula, even though this is not exactly the Shenyao-Zhang equation, there is a formula for this new metric, thinking of the induced metric on a graph, which gives you essentially non-negative scalar curvature. So you could think of this type of space-time harmonic function as giving a deformation to a place where you almost have non-negative scalar curvature, and then can apply the Riemannian versions of such results. They're just like Shane and Yao did. But this has not been completely really exploited yet, but it's something of interest. Okay, so we found the correct equation, and now we want to try and apply it to obtain a space-time version of the positive mass theorem. The main problem are the level sets. As before, we had to take an exterior region using Huisken-Elmanin's result that has trivial topology. Unfortunately, in the space-time setting, it's not known if, say, outside the outermost apparent horizon, whether or not you have this trivial topology. But we were able to get around that by passing to covers. And so we defined something called a generalized exterior region, which in a sense, you go to a covering and cut off some apparent horizons. And then outside that realm, you have a zero first Betti number. So here's a heuristic here. If we start with some asymptotic initial data set, there's a result due to Anderson, Dahl, Galloway, and Pollock, which says that we can induce positive scalar curvature on the manifold with the end compactified. And so at that point, we know that we're connected sum of handles, S1 cross S2s, and maybe some space forms, but those are not so important. So we really want to get rid of these handles. We don't want these non-separating two spheres. That can cause problems for the level set approach. So we want to cut these in somehow. So we pass to, say, some finite cover, and then we have two asymptotic ends, one here, one here. Then there must be some mots in the middle, some apparent horizon that separates the two ends. And so we show that this cuts the Betti number, cuts out these handles, and we end up with a manifold that looks like this, where there are some boundary components now consisting of apparent horizons. And now we can follow the approach on a manifold that has zero first Betti number and not worry about the level sets. Okay, so the only thing left to do is to find what kind of boundary conditions to place on the apparent horizon boundaries. And here we don't use Neumann boundary condition, but rather a constant Dirichlet boundary condition. And this is something that we have to fine tune. We have to pick the correct boundary conditions in order to get a sign for the normal derivatives on these components, and also to find at least one point where the gradient vanishes. And then we can do the Hopf lemma and maximum principle arguments to outlaw any level set which is homologous to these boundary components. And then we have the same situation as before, and we obtain a version of the space-time positive mass formula, where here, instead of scalar curvature, we get a dominant energy condition term. And again, we're integrating not over the manifold, but over a generalized exterior region. Now, in the case of equality, we don't have splitting, as I said before. This Hessian here is a generalized Hessian. I think I have it actually on a previous slide. So we have a generalized Hessian that involves the second fundamental form. So the manifold does not split, but this actually splits the space-time in which this object embeds in the case of equality. This follows, let's say, the big and crucial proof using spinners. It's very similar. We took their ideas and we're able to use it with these harmonic space-time harmonic functions instead of the harmonic spinners to get splitting. Okay, so I think I mentioned most of these comments here. What I'd just like to say is that, well, this is the standard asymptotically flat space-time positive mass theorem, but there are hyperboloidal versions where K tends to G. This is tending to an umbilic slicing of a hyperboloid in Minkowski space, for instance. This version of the positive mass theorem is also susceptible to these space-time harmonic approaches. There's a version with charge and also with torus infinity that are possible. Let me maybe, I think, I wonder how much time I have. I should probably skip this charge case and maybe just say a brief word about the toroidal infinity.
You have 10 minutes.
Oh, 10 minutes. Okay, so let me skip all of this. I will skip all of this. And
oh, wait. Sorry.
I didn't get any of,
just take the time you wanted to take.
I just didn't get, it's fine. These are just what
it's
I wanted.
More than 10 minutes. You have time.
That's fine. There's just a lot more. I wanted to get to the Riemann geometry applications for this seminar.
Okay.
I think it's more than 20 minutes because
it's more than 20 minutes. I'm sorry because you started late.
yeah.
Okay. Take the time you want to take.
Okay, I'll just say one word about these because this is related to a conjecture that should be hopefully proven sometime soon. So there are these exotic type of positive mass theorems where you can have an asymptotic infinity, say conformal infinity. This is asymptotically hyperbolic, locally hyperbolic, where the conformal infinity is a torus or some other genus surface. And the simple, let's say, take the simple type of asymptotics of the metric. You have a tensor that appears in the asymptotic expansion for the G and K. You have different tensors that appear. This is, say, if you take an asymptotically flat realm, you take a Schwarzschildian end, and you see the mass appearing explicitly. Well, here there are these mass aspect functions. These are actually tensors on the conformal infinity, and you want to take a trace of these tensors, and you get something which you can refer to as the mass. Now, these can be motivated by physics. Again, there's a way to motivate these, and one wants to prove analogous type of positive energy theorems for these type of objects. So here we're going to talk about the torus case, where the conformal infinity is a flat torus. And we need to add some extra conditions, say on the topology, to take care of the level sets, because here we're not going to use asymptotically linear functions. It doesn't even make sense in this space. But asymptotically radial functions, where the level sets are thought of as these tori that extend out to infinity. We need some extra topological conditions, say it's a homotopy condition, which says that we have almost a retraction to the conformal infinity. This controls, so we don't have these spherical level sets that block infinity from the interior boundary. So a simple example of a manifold like this, take a connect sum with any closed 3 manifold, and you have some torus band, say. This would be an example where this homotopy condition is satisfied. So we were able to establish a positive mass theorem in this realm for spacetime, the spacetime case. All previous studies involved the case where k is either 0 or equals to g. In this setting, we have, again, the Dama energy condition, but something very important is that we must have a boundary. The boundary is not empty here. And then we have the usual homology condition, and we need the boundary to be the trap surface or a parent horizon. And in this setting, we can establish non-negativity of the energy. There is a corresponding rigidity result, but it's on another slide. I'll kind of ignore it here. What I want to say is that we need the boundary because there are counterexamples, and this is related to the main conjecture in this area. There's the Horowitz-Myers geon, which is a complete metric on a disk, so solid torus, disk across a circle. So this is the boundary is the conformal infinity. Has scalar curvature -6, and this arises as a static solution to the Einstein equations with negative cosmological constant. These are type of soliton solutions. And this object actually has negative mass. So if you don't have a boundary, then well, you cannot necessarily satisfy a positive mass theorem. But the conjecture is, this is the Horowitz-Myers conjecture, is that if you are asymptotic to one of these Horowitz-Myers geons, and you have scalar curvature greater than -6, like the traditional hyperbolic positive mass theorems, then your mass should be greater than or equal to that mass of that Horowitz-Myers, and equality if and only if you agree with Horowitz-Myers. So we weren't able to establish that, but these level set techniques seem to be tending to that direction. So I wouldn't be surprised if this conjecture is satisfied or proven not too long from now. So there are other results in this realm. Just to mention, Crucial, Galloway, Gwynn, Petz prove that the mass aspect function has if it has a sign, then you get the correct positive mass theorem dimension 3. Leah Neves studied this and showed that the mass aspect function has a positive supremum. And all of these are the case when k is equal to g. And then there are some perturbation results, assuming axisymmetry, say, and also Huang and Zhang treated the rigidity case when E is 0, you get a splitting. Okay, let me move on to some applications to comparison geometry. So here, I probably don't need to say this for this audience, but the motivating ideas here is the notion of enlargeability due to Gromov and Lawson. So this is an obstruction to positive scalar curvature, and the heuristic is that if you have positive scalar curvature, you should not be able to pass the covers that extend in every direction an arbitrarily large amount, because based on the heuristic of Bonnet-Myers, if you have positive scalar curvature, the manifold should contract in at least one direction or be small in at least one direction. So, for instance, this is the heuristic reason why the torus does not emit positive scalar curvature. And these type of ideas can be exemplified with the torus band width inequality. So if you have torus band, because the cross sections can expand to covers, very large in this cross directions. In the radial direction, the manifold should not extend too far. And so there have been recent work by Cecchini and Ziedler who have using Dirac-Callias operators that have expanded on this idea, and Arada via mu bubbles, and Chaim Wan for also using space harmonic functions in this direction. So let me say a theorem that we obtained in this direction. using spacetime harmonic functions. So the idea is that we have a general Riemannian band. This is just a three-manifold with a decomposition of the boundary components into different pieces, one positive realm, one negative, just to give them names. And we assume that the second homology has no spherical classes, again, to help with the level sets, the topology of the level sets. And then assuming that the scalar curvature is positive with the usual 6 lower bound, we have an estimate for the width, the distance between the two boundary components, a precise estimate in terms of the mean curvature, minimum mean curvature of the boundary. Now, one can get the traditional version of this with the scalar curvature on the right-hand side. Instead of the mean curvature, one can take h naught to infinity, you get pi over 2. And there's a rigid statement here for these torus band inequality. So this is something that I just want to show the proof using spacetime harmonic functions. This result is essentially was already known, but the idea is quite interesting, and it has elucidates a connection between the three approaches of Callies operators, mu bubbles, and the spacetime harmonic functions. So the idea is we start with a three-manifold, but we can append a fake initial data set, and we will choose our second fundamental form to be a function f times the metric. So it's an umbilic initial data set where f is just an arbitrary function, say potential to be determined. So in that case, if k is this form, then we get the spacetime harmonic equation that looks like this. 3 times f is the coefficient. We solve this equation where the function u has Dirichlet conditions 1 on one of the ends of the components and -1 on the others to get a non-trivial spacetime harmonic function that foliates the level sets foliate this manifold. And then applying the analog of the mass formula in this realm, we get certain boundary terms, and then a bulk term which should be positive, and then some Euler characteristic terms. Now, because there are no spherical level sets, the Euler characteristics should be non-positive, and then this contributes in a good way to the inequality. So we can ignore this term for now. And then the idea is to choose the function f, as is usually done with mu bubbles and Callies operators, choose the function f to blow up at the opposite ends, blow up to positive infinity on one end and minus infinity on the other end. And once you do that, then the signs of these boundary terms are all negative. I mean, they all have the correct sign. So what you get is that this bulk expression is non-negative. This bulk expression is less or equal to 0. And then you just have to choose the correct function that does that, which satisfies an ODE, then this will be non-negative, and then you get a contradiction if the manifold is too long. So you can't, when you solve this ODE, if the manifold is too long in the correct direction, then you're able to make the functions blow up and so forth. So the solution to this ODE depends on how long manifold is. That's how you get the contradiction. But what I want to point out is that this expression that appears here, if you write it from the spacetime harmonic function approach, is the dominant energy condition. So this expression here is just saying that you have 0 dominant energy. You take the lowest value for the dominant energy condition. And in the Callies operator approach, which is essentially, it is exactly the same as Witten's proof of the spacetime positive mass theorem. If you take this version for the second fundamental form in his approach, you will get the same expression and can exploit it in the same way. And so there's this connection between umbilic initial data sets, the Callies operators, the spacetime harmonic functions, and also I can say for mu bubbles, the mu bubble equation would be h equals to f, and so then here you have essentially a apparent horizon or a MOTS. So the mu bubbles are MOTS in these initial data sets, and the Callies operator are the spinor connection modification that Witten utilized. And so there's just this connection where you can get Riemannian geometry results from this space-time version of all three, or in space-time interpretation from all these three approaches. Okay, maybe I think I have 5 or 10 more minutes. I just want to mention some other applications. There's a black hole existence result, which is quite interesting due to Shan and Yao in 1983. Right after their positive mass proofs, they were utilizing the Zhang equation. They found, well, this is the physical heuristic is if you get too much mass, say the mass gets very large in a region of fixed size, so you satisfy an inequality like this, then the gravitational force is too strong, you must have collapse. And mathematically, the way we can interpret this is that there must be an apparent horizon. So if there's too much mass and you keep the size of the region fixed, then you should find an apparent horizon. So they wanted to qualify this and prove that conjecture, which was originally due to Kip Thorne. So the idea is they developed a notion of size called the Shanyow radius. And if the Shanyow radius is bigger than a lower bound for the dominant energy condition, which you can think of as a lower bound for scalar curvature, so you keep that fixed, or let's say increase this. So increase the, remember, scalar curvature is the mass. You increase this and keep the radius fixed, then you should get an apparent horizon. And I write the inequality like this because this is related to the bandwidth estimates that, which is the way you can establish these type theorems. So in this direction, we were able to obtain spectral torque band inequalities, and these spectral torque band inequalities give rise to these black hole existence results. That was the initial approach of Shanyow. So we wanted, the impetus for this sequence of results was to obtain a higher dimensional version of the Shanyow black hole existence problem. So the first step is to obtain a spectral torus band inequality. So we defined a C spectral constant, which is just, you can think of as the first eigenvalue of the Schrodinger operator, where C is just a random constant. And it doesn't have to be, I mean, these can be open manifolds, incomplete manifolds. This definition still makes sense. But in this traditional setting where you have boundary, this would be, say, the zero Dirichlet boundary condition first eigenvalue for the Schrodinger operator. And for the black hole existence results, the C equals -1, C equals 1/2 is the important value for this operator, but other values, they appear in the Yamabe problem. This type of spectral constant appears in many problems in geometry. And so the result that we were able to obtain, again, with spacetime harmonic functions is the following. Here we just have an open three manifold. The ends, we don't need to be complete or any assumption of that nature. And we have a separating hypersurface that decomposes the ends into positive and negative collections. And the usual no spherical classes assumption is assumed to control level sets. Then we're able to estimate the distance from the separating hypersurface to each of the ends in terms of a precise constant involving C and the spectral constant. Okay, so we think of the spectral constant as a weak positive scalar curvature assumption. And so we were able to get bound, this is think of it as a bandwidth estimate. The larger the value of the lower bound for scalar curvature, the smaller this distance is. So it gives the enlargeability heuristic. And there is a rigid statement that we're able to prove because this is one of the nice properties of spacetime harmonic functions that you can get splittings. Here, you don't have vanishing Hessian, but you have a Hessian which is proportional to the metric. And so from Cheer Holdings' work, you get a warp product splitting naturally that comes out where these are flat torus metrics in the cross sections. Okay, so there's some interesting aspects of the case of equality that they have completely different behaviors if you choose different values for the C and the spectral constant, but the one we are interested in, we'll use a C bigger than 1/4. So let me, I'll skip it. We were able to generalize also, but not using spacetime harmonic functions, using a mu bubble approach. Also, we use Callice operators to generalize some bandwidth inequalities to the spectral realm, and this is the black hole existence result that resulted. So we can define a new type of radius. Here, this torcal radius is the soup of widths of all over torcal bands that isometrically immerse into some compact domain. So I think we have a three n-dimensional compact domain in an initial data set. We want to look at all possible torus bands or over torcal bands that immerse into that, and we calculate their widths. That's the torcal radius. Alternatively, one could consider cubes, and we can use the spectral cube radius estimate, the generalized result of Gromov and Wang, Shi, and Yu. And so with this type of radius, we get a black hole existence result, which it says, again, if you have this dominant energy condition very large, okay, which means you're putting too much mass in a region of fixed size, if you keep the radius fixed, then an apparent horizon occurs, and we're even able to estimate the size of the apparent horizon, because the apparent horizon is produced by a blow-up of Zhang's equation, and it has a natural stability associated with it. And from the stability, you get a spectral inequality as well, a spectral lower bound for the scalar curvature of that apparent horizon, and then we can apply the spectral radius estimates to get control on the size of that apparent horizon as well. There's also, so I mean, there's just well, a lot to say, but there's also a quasi-local mass that we were able to define with space-time harmonic functions. It gives a local proof, which is completely different than, say, the Wang-Yao mass or the Sheetham proof of positivity Brown-York mass. It's just completely contained inside a compact set, and so it has some advantages where we're able to define quasi-local masses for surfaces that are not just topologically spheres, which traditionally has been the case in the previous examples, but we can define quasi-local mass in terms of for any surface of any genus, as long as they have embeddings, isometric embeddings to Minkowski space. But I think I've gotten to the point where I should stop. It's just going to take too much longer. The other results that I would mention, but I think Brian is going to mention in the next talk, there are several other comparison geometry results that arise from this method of argument, and one of them is the Ural, a quantitative version of Ural theorem that Brian will mention. I will here, and I'll just stop here and let Brian take over from there.